Good afternoon. Thank you everyone for joining me today. My name is Jonathan Royce. I'm the Global Business Leader for Chromatography Resins at GE Healthcare Life Sciences. And today I'm here to present an evaluation of a next generation protein A chromatography resin for the purification of monoclonal antibodies. I'll start my presentation today with a short introduction. And first I'll just talk about a bit about the biomanufacturing market and where we see that the market has grown to today and where we expect it will be in the future. So as you can see on this slide, monoclonal antibodies have grown over the last decade plus to be roughly half of the biomanufacturing market today. We expect that this growth is going to continue to grow over the next several years. Much of this is due to a strong pipeline of mAbs that are in phase 2 and phase 3 clinical trials. And also because there are many blockbuster patents that are expiring in the next few years, which will put a large focus on biosimilars for some of the first generation antibodies that came to market in the 1980s. There's been a synergistic evolution of monoclonal antibodies in the market and protein A resins. And the graph you see on the left-hand side of this slide is adapted from some work that was done from a research team at Amgen, where they looked at the improvement of protein A productivity and capacity over the last roughly 30 to 40 years. Protein A has without a doubt been an important part of the success of monoclonal antibodies in the market because it has made these types of therapies highly manufacturable and easy to develop in the lab. So the idea of a purification platform, which was enabled by protein A, has really been a key element in the growth of this market. As you can see here, since 1978, the productivity of protein A resins has increased more than 4% annually, and the capacity has increased close to 6% annually. So there's been quite a development in both of these areas. That said, there are still challenges that remain, and those challenges present opportunities for us to improve the technology. The first challenge is that upstream titers have improved dramatically over the same time period that I showed on the previous slide. So upstream titers over the same period have grown approximately 100-fold. And that means that protein A has started to become the rate-limiting step in many downstream purification suites. Protein A columns are also in general too large, which means that they either limit the use of pre-packed technology or they create a mismatch between the protein A column and downstream operations. Either the protein A step takes too long or the protein A column is much larger than its counterparts in the secondary and tertiary steps of the process. Protein A columns are also more prone to bioburden contamination than really any other step in the downstream process. Protein A resin is a reused raw material. It's exposed to the highest load of nutrients as the entire harvest from the bioreactor is loaded onto the protein A column. And it also is cleaned with the weakest clean-in-place chemicals compared to any of the other downstream steps. So whereas normally one cleans ion exchange and HIC resins with 1 molar sodium hydroxide, in the vast majority of cases today, protein A is still being cleaned with 0.1 molar sodium hydroxide. At the same time, regulatory agencies are increasingly interested in sources of bioburden and the methods that manufacturers are using to limit the outbreak of bioburden in their manufacturing areas. So there's an increased level of scrutiny in this particular space. And finally, of course, protein A is always identified as an expensive step in the manufacturing process. And despite generational improvements that have led to lower cost of ownership and lower costs in manufacturing, there are still further cost reductions needed. So some of these challenges can actually be addressed through simple process design. And I'm going to first walk through a few areas where processes themselves can be modified in order to improve protein A productivity. Several years ago, we introduced a technique for one of our resins, mAbs that we call variable loading time. Variable loading time is a way to better utilize the capacity that's available in a resin while minimizing the amount of time needed during the load step. The technique is quite simple. Rather than load the column at a constant resonance time, one loads the column at an increasingly, or in a stepwise decreasing fashion in terms of speed. So one starts with a very short resonance time, and as the resin starts to reach its saturation point, we then slow down the feed pump. We run again until we near the saturation point, and then we slow down again. In this particular example, you can see here we've chosen 3 different residence times for the load, which lead to a shorter average residence time overall, but maintain the capacity one would get with a longer residence time. And as the load step tends to be one of the longer unit operations during protein A chromatography, you can get significant improvements in productivity. In this case, we were able to demonstrate close to a 40% productivity increase with maintained capacity and purification performance. Another way protein A productivity can be improved is by implementing continuous chromatography. And there's a lot of focus on this in the market today. There are many research and process development labs that are investigating continuous capture, especially for protein A. Continuous capture, of course, offers the advantage of improved utilization of the available capacity in the resin, which leads to smaller equipment and in many cases shorter process times. There's less manual handling required, or as another way to look at that is that there's more automation generally implemented, which reduces manpower requirements. And it also makes it possible to manufacture smaller batches to scale out instead of to scale up. And this technology can be combined with other technologies, one of which is shown here in the last bullet point, straight-through processing, where multiple chromatography steps are connected together without hold tanks to reduce wasteful steps in the process that lead to increased process time, and also to push QC methods online instead of offline. And finally, one can reduce the number of purification steps in a process in order to improve overall productivity. And this is an area we've worked on intensively over the last decade. We've worked quite a bit with customers to look at options for combining, for instance, the effect of a cation and anion exchange step, separate cation and anion exchange steps into a single multimodal step that provides the same purification performance but reduces a column in the downstream manufacturing area. But despite these process changes, we still feel that there have been advantages or improvements that we can make in the actual resin itself. And so we've worked quite intensively over the last several years to address resin performance and to develop a next generation version of protein A. We started by looking at the ligand itself that's used in mAbs like Shore. And here we had a goal to increase the alkaline stability to improve the ability to clean protein A with chemicals that are at least as concentrated as those that you use today in ion exchange and hydrophobic interaction chromatography. We did this by going back to the monomer of Shore. Shore is actually a tetramer, as many people know. It's a single domain that's been built into a tetramer. And we went back to that monomeric version and started to look at weak points in the protein A molecule to identify possible mutations we could make that would improve alkali stability. We did this using a high throughput screening approach. And the key to this entire screening and evaluation exercise was the BioCore SPR technology. So the BioCore technology allowed us to evaluate different modifications to the protein A ligand without having to actually synthesize resin and do on-column experiments. And this meant that we could apply a design of experiments approach where we generated libraries of ligands, looked at possible changes for improvements in alkali stability, and then iteratively improved the ligand over time to end in a construct that is highly alkali stable. And during this work, we actually evaluated more than 400 different constructs before we settled on a final design. We also looked at the base matrix, or the bead that we use for our protein A resins, and thought a lot about how the original mAbs Shore bead was designed and what challenges it was really designed to address. So mAbs Shore was developed at a time when many processes were at relatively low concentrations coming out of the bioreactor, and flow rate in the Protein A step was one of the main limitations. Today, most processes are relatively high concentrations, and in fact, mass throughput is the limitation in a process, not volumetric throughput. So we started to think that there's opportunities to optimize a new bead for Protein A chromatography, and we also decided that it would be opportunistic to co-optimize both the ligand and the bead together. And here you can see one of the exercises that we performed during that co-optimization. So on the right-hand side of this slide, you see an experiment where we used a base matrix that had very large pores, and we actually varied the ligand density on that bead and also the length of the ligand. So we worked with both tetramers, hexamers, and octamers of our ligand. What you can see on the left-hand side is that for this bead with very large pores, as you increase the ligand density for both the tetramer and the hexamer, you get higher binding capacity. And that makes sense. That's what one would expect to see that result. You also see that the octamer, the longest ligand, actually doesn't give that response. If anything, there's perhaps even a slight decrease in capacity as you increase ligand density. This is due to steric differences that occur in the pores inside a bead. So as you get to longer and longer ligand constructs, the ligands themselves take more space in the pores, and as IgG binds to that ligand, the complex of IgG and the ligand itself also takes more and more space. And eventually you reach a point where the pores are so crowded that you start to limit diffusion of IgG into the bead itself. This result is confirmed by the experiment shown on the right-hand side of this page, where we used a bead that had very small pores. And here you can see we worked with only the tetramer and the hexamer, and we could show that for the tetramer, we could get some improvement as we improved the ligand density, although you see in the last two blue points here that you get somewhat of a plateau. And that for the hexamer, we actually reached an optimal where when we went beyond the medium ligand density, we actually saw a progressive decrease in performance thereafter. The result of all this work has been a new generation of Protein A resin that we call mAbs Prisma. mAbs Prisma is really built on the heritage of former mAbs products, but it's a completely new bead and new ligand that were really designed for modern processes. It offers improved binding capacity to resolve these bottlenecks that are occurring in production. It offers exceptional alkaline stability for cleaning and sanitization operations, and it's been really designed from the start with an extensive security of supply package in mind. And now I'll present some slides on the actual performance of this resin. So I'll start by talking about productivity and process efficiency. Here you can see a comparison of mAbs Prisma to mAbs Shore and mAbs Shore LX, tested at different residence times and measuring dynamic binding capacity. And what you can see here is that mAbs Prisma, this co-optimization of the ligand and base matrix, has really given very good improvements in terms of dynamic binding capacity at all residence times. So regardless of whether you run a continuous process where residence times tend to be quite short, or you're running a large-scale batch process where residence times tend to be quite a bit longer, you get a significant improvement, anywhere on the order of 25 to 40% improved capacity versus mAbs Shore LX. And today, we can say mAbs Prisma, at longer residence times, has a capacity that's very much on par with ion exchange and HIC resins that are used in the remaining parts of the downstream process. As you can see here, approximately 80 grams per liter. We've also developed the new bead to really meet the needs of today's processes in terms of flow rate. And here you can see some data from a large-scale column and Oxychrome 300 that's been packed using mAbs Prisma, where we've measured both back pressure and flow rate to understand the relationship between the two. And as you can see here, mAbs Prisma offers very high flow rates at relatively low back pressure, and does this with a bead that's approximately 30% smaller than the one we use today in mAbs Shore. The combination of this capacity, higher capacity, and optimized flow rate performance offers significant improvements in terms of productivity from existing equipment. An improved productivity means that ultimately, if your plant is in a situation where you need to make capital investments to, for instance, purchase larger columns, you can actually delay those investments by making a change to mAbs like Prisma. On the left-hand side, you can see a comparison of the mass throughput on an Axichrome 450, a 45 centimeter column, using mAbs like Prisma, mAbs like Shore, and mAbs like Shore LX. You can see that the mass throughput increases somewhere on the order of 25–50%, depending on what your benchmark is. You get a similar relationship if you look at volumetric throughput and look at the maximum size bioreactor that you could harvest using that column. So here you can see mAbs like Prisma could harvest, using a 45 centimeter column, a 2,000 liter bioreactor with a titer of 4 grams per liter, whereas mAbs like Shore LX and mAbs like Shore would require larger columns for the same bioreactor. Another way to look at this is to think that if today your plant isn't productivity restricted, that you can actually use this advantage to reduce the cost of consumables. So here you can see advantages both in terms of resin consumption savings and buffer consumption savings using the 3 different resins. And again, you can see here an improvement somewhere on the order of 20–33% in terms of both resin and buffer consumption. I mentioned before that mAbs like Prisma also offers significantly improved alkali stability. So let's look at some of those results. Here you can see a comparison of mAbs like Prisma against mAbs like Shore LX and mAbs like Shore when cleaned with half molar sodium hydroxide. Each cycle here represents 15 minutes of contact time. What you can see is that mAbs like Prisma retains more than 95% of its dynamic binding capacity after 150 cycles, whereas mAbs like Shore LX has lost nearly 20% of its binding capacity, and mAbs like Shore has lost more than 30%. This means that when designing processes, the capacity that you measure at cycle 0 is more available even after repeated usage as compared to mAbs like Shore LX and mAbs like Shore. Or another way to think about it is that safety factors can be reduced, thereby shrinking the size of your columns. If improved cleanability or resin cleanliness is a goal, you can also increase sodium hydroxide concentration to as high as 1 molar. And here you can see a comparison of mAbs like Prisma and mAbs like Shore LX, cleaned with now 1 molar sodium hydroxide, again with 15 minutes in each cycle. mAbs like Prisma retains more than 90% of its dynamic binding capacity, and mAbs like Shore LX retains only around 50%. This can be an important improvement in terms of performance if you want to, for instance, align your clean-in-place solutions throughout the entire downstream suite, or you want to have better control of bioburden or potential cross-batch contamination. Sodium hydroxide is a very good sanitizer for most forms of bacteria, but one area where it's not as effective is with spore-forming bacteria. And here you can see the results of a oxidizing agent that we've been investigating for mAbs like Shore and have recently developed a recommendation on for resolving a spore-forming bacteria contamination. The chemical we use is called peracetic acid. It's used in very low concentrations. This is a common chemical already used for sanitization, cleaning and sanitization of UF cassettes in downstream manufacturing. And you can see here with the green and blue lines, which are somewhat hard to distinguish, but they're both on the left-hand side of this graph, that they offer almost immediate reduction of spores with very short contact times. We have an official recommendation today from mAbs like Shore that this treatment can be performed 2 to 3 times over the lifetime of the resin, and we're currently generating data to extend that recommendation also for mAbs like Prisma, and we feel confident that we'll be able to substantiate that recommendation shortly. So what about purification performance? Let's look at a study that we've done using 2 of our in-house mAbs where we've compared the purification performance of mAbs like Prisma, mAbs like Shore, and mAbs like Shore LX. I'll point out on the left-hand side of this slide that the load values for the 3 different resins are quite different, where mAbs like Prisma has been loaded with approximately 50% more mAb due to its higher dynamic binding capacity than both mAbs like Shore and mAbs like Shore-LX. Here you can see on the top the 2 mAbs that we tested and a comparison of recovery or yield, and you can see that in all 3 cases we have very similar performance. Host cell protein levels are shown in the eluate pool at the bottom of the slide, and again, very equivalent performance between the 3 resins. On the top of this slide, you can see a comparison of aggregates. One thing to note here is that you do see slightly higher levels of aggregates with mAbs like Prisma at these much higher loadings. That's to be expected when you load a resin with 50% more mAb, that you also can expect to see somewhat higher levels of aggregate. And we have confirmed that if you load these resins at similar loading levels, you get similar aggregate clearance. We're currently working on methods to reduce these levels even at high loading via some specific wash and elution techniques, and we hope that we'll be able to present those in the first half of next year. At the bottom of this slide, you can see DNA clearance on the 3 resins, and again, you can see that they're very equivalent. And finally, if we look at pool volumes, here you can see, again, equivalent performance across the 3 resins, and leached protein A, quite similar values, although you do see slightly higher values of protein A for the resins that have higher ligand density. So mAbs like Prisma has the highest ligand density on this slide, and therefore the highest leached protein A values. mAbs like Shore-LX is an intermediate in terms of ligand density and protein A leakage, and mAbs like Shore being the lowest in both cases. This is expected, but in all cases, we believe these values are easily handled by the secondary and tertiary steps in a downstream purification suite. As I mentioned at the introduction, we've put extended measures into mAbs like Prisma to really ensure strong security of supply. And so from the start, we've designed this product to have both sorts of agarose validated into the manufacturing, and also 2 sources of the protein A ligand. We've taken steps over the last few years to develop in-house manufacturing of protein A ligand, and mAbs like Prisma is the first product that will be produced using in-house manufactured ligand, as well as ligand that's produced by a contract manufacturer who performs a GE-developed process. So we have true redundancy of the ligand manufacturing for this product. So finally, I'll go through a few conclusions. As I discussed, productivity can be improved in mAbs downstream processing, both by process design improvements, but also by improvements in resin. mAbs like Prisma has been developed to really address some of the challenges that we have today. And it's a new high-capacity resin with resistance to 1 molar sodium hydroxide that really is designed to solve both productivity and bioburden issues. It offers significantly higher binding capacity, which gives improved mass throughput and productivity, especially when looking at existing equipment and trying to get the most out of your existing capital. Thank you for your time. I look forward to answering any questions. How's that?